Alright, welcome to Unit 7 for AP Environmental Science. Unit 7 is all about atmospheric pollution, and we're going to be going through the 8 topics for this unit. We'll have 8 separate videos, one for each of these topics, so the introduction to air pollution will be this video here. Then we will go into photochemical smog, thermal inversion, atmospheric carbon dioxide and particulates, indoor air pollution, reduction of air pollution, acid rain, and noise pollution. So that'll start us with the introduction to air pollution. And here we go. So we watched this video in class. This is all about the smog in Delhi, India. If you guys remember, if you haven't watched the video or you weren't in class or you don't remember it, just go to this link and you'll be able to check out that video. So essentially when we're talking about air pollution, we are talking about a global system of air pollution because air pollution doesn't just affect local small systems. Typically when air pollution enters the atmosphere, it's going to eventually get into a global system. And the basic definition of what air pollution is just the introduction of chemicals, particulate matter, or microorganisms into the atmosphere at concentrations high enough to harm plants, animals, and materials such as buildings or to alter ecosystems. So there is an important number there because yes, there is some air pollution that gets in, there's some chemicals, particulate matter get into the atmosphere that's normal, natural, and okay. It's when we get it to a high enough concentration that we start to see harm. Now when we look at different types of pollutants, we are looking at natural pollutants, pollutants coming from an area, pollutants coming from stationary spots, and then mobile pollutants. And you can kind of get an idea from this image, all of the different sources that we can have. Natural, of course, wildfire, forests, volcanoes, and lightning. Areas would be cities or farms. Stationary could be power plants, sewer treatments, industrial areas, and then mobile would be transportation for the most part. So in 1970, the Clean Air Act was put into place to try and control the air pollution on a national level. The goal was to enforce regulations overall to help prevent the general public from becoming harmed from the different air pollutants. So, this really does a lot to try and prevent different air pollutants and save lives. Believe that there's 1.5 billion people breathing dangerously high levels of pollution every day in the world. The EPA estimates that 160,000 deaths were prevented since the Clean Air Act amendments were put in place, and that was in 2010. So the Clean Air Act, which we'll look in a little more detail, has done a lot, but of course there's always more that can be done. So this just gives you an idea. Before the EPA Clean Air Act, the suspended particulates and the pollution levels in different cities, you can kind of you get a feel from just this graph of how much pollution there really was in the atmosphere. And this was from 1968 to 1972. So it's obvious from this image that the Clean Air Act was necessary. Now there's 6 outdoor criteria pollutants that the Clean Air Act really goes into regulating. And you can remember this by remembering nose clip, because a nose clip will save you from air pollution. Nose clip is going to be for nitrogen oxides, ozone, and it's important that you know that that's ground level tropospheric ozone, not the stratospheric ozone. Remember that tropospheric ozone is bad, stratospheric ozone is good. It also goes for sulfur dioxide, carbon monoxide, lead or other toxic materials or toxic metals, and particulate matter. So just remember nose clip to remember those 6 different outdoor pollutants that are regulated. So how do we classify pollutants? Well, the Clean Air Act actually identified those 6 that harm humans in the environment. They come from many different sources, so you have to keep in mind that when we're looking at those, the regulations go in place for many different sources. Now, obviously, there are natural sources where these can come from, and there's no real way to regulate that, but we can regulate and try to control the amount of anthropogenic pollution. So we'll go into each one of these in a little bit of detail here. We'll talk about them later as well, but nitrogen oxides would be nitrogen monoxide, nitrogen dioxide, and also dinitrogen monoxide, which we'll look at too. Nitrogen oxides come from vehicles and fossil fuel combustion. They can also come naturally from forest fires, lightning, and soil, if you guys remember nitrification when we talked about soil mechanics. And then respiratory, the reason that these are important is because they're respiratory irritants. They can also help to cause acid rain through the creation of nitric acid, and they are part of smog. So you can see from this image all of the different sources, along with how they are transformed in the atmosphere to make more harmful chemicals that cause plants and humans and animals to feel the effects. So ozone is another one. Remember, we talk about ground level ozone, not stratospheric ozone, because ground level, when we're talking about tropospheric ozone, that's the bad stuff. So the type of ozone, well, when we're talking about ozone, ozone is always the same. It's O3. Good ozone, bad ozone. It's O3. The difference between the good and the bad is good ozone is in the stratosphere because that helps protect us from the UV rays being shot down from the sun. And then in the troposphere, it's bad because it's a respiratory irritant and can damage plants. Now we'll talk about specifically the production and how ozone is formed, but it's a secondary pollutant. It's not a primary pollutant. We'll talk about secondary versus primary, but it's a secondary, meaning that it is actually formed after one other pollutant has been released. It's formed from sunlight and water reacting with volatile organic compounds, also known as VOCs, nitrogen oxides, also known as NOx, and then just plain old-fashioned oxygen. So here's an idea, very basic formation. O2 is split by the sunlight, so we get this ultraviolet sunlight that actually breaks oxygen into O plus O instead of O2. It makes it unstable, and the unstable free oxygen will actually bond onto another oxygen. So you get an idea here. We start with O2, the sunlight actually breaks that bond apart, and each of those individual atoms of oxygen can now bond with an O2, making O3. And it's a natural process. This happens in the stratosphere all the time. The problem is nitrogen oxides and volatile organic compounds react in the presence of sunlight as well, which can form this ozone and make this reaction happen at ground level. And that's where it becomes very dangerous. So some of the issues with good ozone, we are seeing, or we have seen, a depletion of ozone layers by CFCs, or chlorofluorocarbons. These are chlorine, bromine chemicals. Typically, they were created, these are your aerosols. Now, what happens is we release CFCs into the atmosphere by industries. They get into the stratosphere, and what they actually can do is they're broken up by the sunlight and then destroy the O3 in the atmosphere, creating O2, which reduces the amount of O3 in the atmosphere. If there's less O3 in the atmosphere, we have less protection from the ultraviolet radiation, which is bad. This hurts humans and plants and animals. Some of the consequences, of course, is an increase in skin cancer by harmful UVB rays, because the ozone helps protect us from the ultraviolet B radiation. It also can cause skin ailments, it can disturb life cycles, and destroy marine life. So when you hear about the ozone hole, or the hole in the ozone layer, it is this process. And what's really scary about this is the CFCs would get into the atmosphere and essentially create this chain reaction of the breakup of ozone. And they would just keep going over and over and over, because the chlorine would break up the O3 to create new bonds, and you would have this huge amount of depletion of ozone. And so there have been laws put in place to try and prevent chlorofluorocarbons from being released in the atmosphere. Some of the bad ozone, remember, this is the stuff that's on the ground level. And essentially, with the release of nitrogen oxides, NOx, through fossil fuel combustion, and VOCs, we see more ozone being produced, because if you take NOx and VOCs together with a little bit of heat and sunlight, you get a lot more ground level ozone directly into the air. It's not emitted directly, but because of those reactions from the nitrogen oxides and the volatile organic compounds, ozone is then produced. And remember, ozone can be an irritant on the ground level. So some of those consequences for bad ozone: it can injure plants. So this is just an ozone injury to 2 different types of plants you can see, as well as causing breathing problems and respiratory problems for humans. And that is one of the big reasons why we should not have as much ozone on the ground layer. So again, respiratory problems, plant damage, and it is, of course, a greenhouse gas because it will absorb the infrared radiation, so it'll actually create a hotter troposphere. So back to our nose clip, we just went over the N and the O. We also have sulfur dioxide. Sulfur dioxides come from coal and oil being combusted. It also comes naturally from volcanoes and forest fires. Sulfur dioxide is a respiratory irritant. It can affect plant tissues, and it also can lead to acid rain. Now, this map here actually shows you where the density in tons per square mile of sulfur dioxide being released. Notice, not as big of an issue on the west coast as it is on the east, and that's one of the reasons why we don't see a lot of acid rain in the west. C for our nose clip is carbon monoxide, which is created during the incomplete combustion of most matter, so it can actually be released through vehicle exhaust or other combustions. And it can be very dangerous if it's indoor with poor ventilation, like burning of manure, charcoal, and kerosene. The reason it's so dangerous is because it can't be seen, it can't be smelled, you can't hear it, but you can put in, of course, a carbon monoxide detector. So basically what carbon monoxide does is it gets into your red blood cells, it blocks oxygen so that you end up suffocating slowly. So some of the danger points indoors: there's many, right? Any heating equipment, any cooking appliances where you're using gas, any fireplace, your chimneys. If you don't have proper ventilation, you're going to find carbon monoxide to be a very, very, very high risk. Then we are on the L. Remember, lead is one of those. It's also other toxic metals, but lead used to be in gasoline. It was phased out by 1996. It's also it used to be used in paint in older buildings, and it used to be used in pipes. You've probably heard of the Flint, Michigan lead crisis. It's toxic to the central nervous system, so that's why it's so important that we don't have lead and other toxic metals introduced into our bodies. And then the P in nose clip is particulate matter. Particulate matter comes from combustion of fossil fuels and biomass. There's much more particulate matter in diesel than there is in gasoline, but it can also be road dust, rock crushing, volcanoes, fires, dust storms. Particulates are basically just like, think of dust. So little bits of tiny particles in the atmosphere. It can block sunlight and prevent photosynthesis if it's heavy enough. It can also get into your respiratory system and cause major respiratory problems. When we talk about particulate sizes, we're looking at PM10 and PM2.5. Anything above PM10 we consider to be large enough that your respiratory system can actually prevent it from entering your body. So your nose and your throat will actually filter it out in your mucus. So when you get boogers, the dirt that's in your boogers is just that particulate matter that's able to be caught. But once you get to the PM10, it can actually get into your respiratory system. Anything at 2.5 and lower becomes very, very concerning because it's so small that it can actually get very deep into your respiratory tract, and it is usually considered to be more toxic. We'll do a lab in class about particulate matter, and we'll actually try to gather some to see how much we're actually being exposed to in different locations. So some other major pollutants are volatile organic compounds, VOCs. VOCs are just hydrocarbons. They can come from building supplies and household products like benzene and toluene and formaldehyde, but we also have plants that release VOCs very naturally. So when we look at VOCs, we're looking at hydrocarbons, and the reason that they're dangerous is because, if you remember, we looked back, they themselves can be toxic, but they also can help in forming more ground level ozone. This is just in a list of more of those VOCs and where you can find them, and they're, if you really want to nerd out, their chemical formulas. But there you can see, just from looking over here, there's so many different sources, but a lot of them are coming from building supplies. And this is why it's really important that when you're working on maybe putting a stain on wood, you always want to make sure you have a well-ventilated area. Mercury is another major pollutant because mercury, as we know, can be a huge nervous system harmer. This is the mercury cycle, where it's emitted into the atmosphere in different processes, particularly coal and oil combustion. It can then be deposited through precipitation, accumulate in different lakes and reservoirs, and eventually transport itself through watersheds, where it will get itself into the food web. And if you guys remember bioaccumulation, where larger and larger amounts of mercury start to build up. So this is just another example of that mercury cycle and how mercury gets into our environment. There's many different sources, and so it's really important that we keep an eye on it. But this is a good example right down here of bioaccumulation, where microorganisms have a little bit of mercury, and then small fish have a little bit. A larger fish will then, because it's going to eat them, have a little bit more, and then these larger predatory fish end up having a larger amount of mercury buildup. And that's why it's important that we limit our amount of seafood eaten because of the bioaccumulation of mercury. Carbon dioxide, of course, is another pollutant, and we'll talk a lot about carbon dioxide, not only in this unit, but also in our global change unit, because there's a direct correlation with global temperatures and the rise of carbon dioxide. Now, remember earlier we talked about primary versus secondary pollutants. On a basic scale, or a basic understanding, a primary pollutant comes directly from a source. So this is a direct pollutant that is released into the atmosphere, okay, like a smokestack or an exhaust pipe. Whereas a secondary pollutant is a little bit different, because a secondary pollutant is where you have your primary pollutant transformed in the presence of sunlight, water, or oxygen, and then creating new chemicals. So for instance, ozone, sulfur trioxide, sulfuric acid, hydrogen peroxide, nitric acid, and PANs, which we'll talk about a little bit. It usually happens in the daytime and in wet conditions because it has the presence of sunlight or water, but these are, again, secondary pollutants that are primaries that are converted into these secondary pollutants. So these are not directly released into the atmosphere. They are secondary pollutants in that they are converted from some other source. So that'll bring us to the end of the first video, all about the introduction. Our next video will be about photochemical smog.